All right, let's go ahead and get started. I do want to welcome you to this video. This is Intermolecular Forces, the first of two installments on intermolecular forces. So let's go ahead and get started. So we're going to start with this molecule here. These molecules here, I should say. There's one on the left and one on the right. And you can see that carbon in gray is bound to nitrogen in blue and oxygen in red and fluorine in yellow, and the molecule on the left. Same thing is true of the molecule on the right, but we're going to focus today on the bonds that hold these molecules together. Those are the dotted lines that you see in the middle. So these are intermolecular forces, and that's the topic of this video lecture. So let's start with some guiding questions. The first thing we want to ask is, how do intermolecular forces compare in strength with the metallic, ionic, and covalent bonds? So we've looked fairly extensively at metallic, ionic, and covalent bonds, and we want to see how intermolecular forces compare in strength. What is the scale, in other words, of metallic, ionic, and covalent bonds as compared to intermolecular forces? Next, which are the weakest of the intermolecular forces? So we know that intermolecular forces are weak, but which is the weakest of all the intermolecular forces? And there are three that we're going to talk about today. Next, what characteristic of water does hydrogen bonding explain? Water, as it turns out, is a fairly peculiar molecule. It's strange in a number of different ways. We want to know how hydrogen bonding explains these characteristics of water. So, intermolecular forces are also known as van der Waals forces. So when you see van der Waals forces, you know we're talking about weak intermolecular forces. And we're going to talk again about three of them. They are much weaker than intramolecular forces, which include ionic and covalent bonds. So there's the scale then. Ionic bonds quite strong, covalent bonds also strong, intermolecular forces of the type we're going to be talking about today, significantly weaker. All right, let's take a look at this molecule right here. It's hydrochloric acid. Hydrochloric acid, or HCl, has an electronegative end and electropositive end. That makes it a dipole. And when we have dipoles in the presence of other dipoles, like other hydrochloric acid molecules, then we're going to see dipole-dipole interactions. And that's what you see in blue. These are the hash marks that you see in blue. So chlorine, which is electronegative, and hydrogen, which is an electropositive atom on a separate molecule, are going to interact. And that interaction is called a dipole-dipole interaction. As you can imagine, if it happens many, many times in a beaker or a test tube, it's going to be quite strong. Now, dipole-dipole interactions are not the strongest of the intermolecular forces. They're not the weakest either. So they're somewhere in between. They're intermediate between two others that we'll talk about. So those are dipole-dipole interactions between an electronegative and electropositive atom on a different molecule. They involve permanent dipoles. Hydrochloric acid is a permanent dipole. In other words, chlorine will always be electronegative, hydrogen electropositive, and whatever it is going to be a permanent dipole. And for that reason, they're typically liquids at room temperature. So the intermolecular force called dipole-dipole interactions are going to cause these hydrochloric acids to pull fairly close together. In other words, the hydrochloric acid is not going to just allow to randomly roam wherever it wants to, but they're going to be held close to each other, thus making these molecules tend to be liquids or more condensed than they would be if these intermolecular forces did not exist. All right, let's look at the second type of intermolecular force, hydrogen bonding. And hydrogen bonding is really just a subset of dipole-dipole interactions. But it happens to be the strongest of the intermolecular forces because it involves three distinct atoms. Hydrogen, hydrogen bound to three atoms, and they are nitrogen, oxygen, and fluorine. So we'll remember those three. Nitrogen, oxygen, and fluorine, when bound to hydrogen, are going to form hydrogen bonds. Strong, very strong, or relatively strong, I should say, intermolecular forces. They are the strongest of the three that we'll talk about. Hydrogen bonding explains the relatively high boiling point of water. We'll see how that works in just a few minutes. It explains the high surface tension of water as well. And it explains the unique density properties of water and ice. As you know, water is the liquid, but it is more dense than ice. When you drink iced tea, the ice will float to the top. More importantly, in a lake or a pond, in the wintertime, ice forms on top and allows the sea life below to live throughout the winter. So that's very important. So most substances are not going to be that way, but water, liquid water, is actually more dense than its ice counterpart. And finally, hydrogen bonding is important in the structure of DNA. So last year we saw that the DNA molecule was it was composed of a DNA double helix with nitrogenous bases, that's adenine, thymine, guanine, and cytosine, bound together via hydrogen bonds. So it's important in the molecule of life, DNA. So I told you I'd talk about hydrogen bonding and how it affected the boiling point of water, and here it is. So what's shown in red, obviously, are water molecules, but they're being hydrogen bonded. Remember, nitrogen, oxygen, and fluorine are the key elements here. When bound to hydrogen, and certainly oxygen is in this case, they form hydrogen bonds. So the blue hash marks then, the blue hash marks are the hydrogen bonds between the water molecules. They hold water molecules very tightly together, and therefore water ordinarily is going to be a liquid. If those hydrogen bonds did not exist, then it would be a vapor at room temperature. And in fact, if you want to boil water, another word for boiling is vaporization. If you want to vaporize water, you're going to have to disrupt those blue bonds, those hydrogen bonds that exist between the hydrogens and the oxygens of water molecules. All right. Water is not the only molecule that does this. This is ethanol. But again, we see hydrogen and oxygen, right? Hydrogen and oxygen are going to hydrogen bond with one another. And so ethanol is also going to have a relatively high boiling point for its size. All right. Hydrogen bonding and surface tension. So let's take a look at this mosquito here. We've always seen this type of situation where a mosquito lands on a surface of water and it doesn't sink. The insect simply walks on the water. How does that happen? Well, if you take a look at water on the surface obviously is composed of a layer of water molecules, and this layer kind of forms a film. So on the surface of the water, like say here and here and here, you're going to see hydrogen bonding, and then hydrogen bonding is going to be very important in forming this kind of film that allows that mosquito to sit comfortably on the surface of that water. Now, if it was something heavier like a rock, of course, the rock is going to fall straight through because of the fact that the hydrogen bonding is not going to be sufficient to hold the rock in place, but certainly can hold lighter things like mosquitoes or maybe a paperclip in place. So it explains hydrogen bonding explains that high surface tension. And finally, let's talk about the last of the intermolecular forces. We've already talked about dipole-dipole interactions, and we've talked about the hydrogen bonding, and now let's go to London dispersion forces. In 1928, an individual, a German American whose last name was London, was looking at gases, and he noticed that gases, when they were cooled to fairly low temperatures, they would form liquids. So it was left to this individual to kind of discern what it was that allowed these gases to become liquefied. And this is the kind of idea that he came up with. What he said was that even though for example, let's take fluorine gas, fluorine, as you see here in red, that even though it was a nonpolar covalent bond, there would be times when the electrons which were involved in the bond would just kind of randomly, because they're not stationary, they're moving around, but they would just randomly accumulate on one side of the molecule. So on this molecule, this fluorine molecule here, for example, we see that just momentarily a dipole is formed. It's an instantaneous dipole. It's not going to last for very long, but it's there nonetheless. And it's going to induce a dipole in a neighboring fluorine molecule. So if on the left fluorine molecule, there's an increase in the number of electrons, kind of like a traffic jam of electrons on that fluorine. On this fluorine, there's going to be a deficiency of those electrons because those electrons are going to be pushed away to the other side. So you're going to, in effect, induce a dipole. And so now you have effectively an electropositive and electronegative into each molecule. And what you see in green is that London dispersion force, or that very, very, very weak interaction that you're going to see between even nonpolar molecules like fluorine gas. So these are known as induced dipole forces because one molecule, which instantaneously and temporarily has this kind of polar is really too strong a word, but a more electronegative end than electropositive end is going to induce a dipole in the next molecule. So induced dipole forces explain the gaseous nature of diatomic elements. Diatomic elements are gases because the forces between them, the London dispersion forces, are just not very strong. In fact, they are the weakest of the van der Waals interactions. All right. They are present in virtually every molecular interaction. So it's not a question of whether it has hydrogen bonds or whether it has London dispersion forces, for example. If something has hydrogen bonds, it also has London dispersion forces. They're just less relevant when hydrogen bonds or dipole-dipole interactions are present. Let's talk about intermolecular forces or van der Waals forces and boiling points. We're going to compare London dispersion forces with dipole-dipole interactions, and we know that dipole-dipole interactions are stronger. So the boiling point of molecules that have dipole-dipole interactions are going to be higher. Hydrogen bonding, even higher, because of the fact that hydrogen bonding is the strongest of the intermolecular forces. Let's take some practice questions. First, which of the following types of bonds is not significant in the boiling temperature of a solution? So we've talked about London dispersion forces. They're weak, but they do contribute to boiling point. Hydrogen bonds, they're strong, relatively strong intermolecular bonds. So those are certainly going to impact boiling point. Polar covalent bonds, no, those are the bonds that are in between that hold the molecule together, but they don't influence the boiling temperature of a substance as does dipole-dipole interactions. So our answer would be C, polar covalent bonds. Let's take a look at another question. Rank the following from lowest to highest boiling temperature. So when we look at these molecules, we can see that C2H6 really doesn't have anything going for it. I mean, it's not hydrogen bonding, it's not dipole-dipole, so it's just going to be London dispersion forces. The second one, C2H5OH, would have hydrogen bonding because of the oxygen bound to the hydrogen. And C2H5Cl, there's a dipole there. So that would be intermediate. So it looks like our answer would be D. So C2H6 followed by C2H5Cl followed by the hydrogen bonded C2H5OH. Let's take one more question. Practice question number 3, which of the following molecules does not exhibit hydrogen bonding? Remember, nitrogen, oxygen, and fluorine are the important molecules here. H2O has hydrogen bonding in it because of the oxygen. NH3, nitrogen is going to be involved in hydrogen bonding. CH4, no, carbon is not one of the three, so that would be our answer. CH4 does not exhibit hydrogen bonding. Hydrogen fluoride, fluorine is one of them, and CH3OH, oxygen bound to hydrogen, will give us hydrogen bonding. So, folks, I hope that is a good introduction to intermolecular forces. Join me on the next one where we'll get into some more important details on intermolecular bonding. So I'll see you on the next one. Thank you.